Good morning, friends. In last lecture, we had seen the problems on beam structure. In that, we have calculated moment of resistance, area of steel, or we have designed the beam problem. That is, we have to calculate the width and depth of the section and steel required for the beam section. Now, in that beam section, the shear reinforcement is required, and that shear reinforcement we have to design in this lecture. So we'll start with design of shear reinforcement. In that, first introduction. When any type of beam is loaded, when any type of beam is loaded with any type of load, that is point load, uniformly distributed load, triangular load, any type of load, normally shear is produced. That is, whatever load is given on the beam, then it can produce a shear force by the variation of bending moment along the span. That this shear force acts or move along the span of the beam through the bending moment, introducing the variations. These bending stresses varies at two cross sections, that is at the junction of beam and column. These are the two sections which produces horizontal shear stress and vertical shear stress. Horizontal shear stresses in beam section and vertical shear stresses in column section. So in that, first shear stress is nominal shear stress, and it is denoted by tau v. This nominal shear stress is always present in any structure. So it is the shear force. Nominal stress is the shear force developed due to designed load acting per unit cross-sectional area. See, nominal shear stress is nothing but it is the shear force developed due to design load acting per unit cross-sectional area. That is, tau v is equal to Vu upon Bd, where tau v nominal shear stress, Vu shear force due to design load, B width of the member or breadth of the member, D effective depth of the beam section. Then second one, shear strength of concrete. When there is a nominal shear strength, there should be a shear strength of concrete. So that nominal shear strength should be bared by this concrete. So shear strength of concrete, it is denoted by tau c. So it is the design shear strength of concrete in beams without shear reinforcement. It depends on grade of concrete and percentage of steel. So the design shear strength of concrete in beams without shear reinforcement is given below, along with for solid slabs. The shear strength of concrete shall be K tau c, where K is the parameter depending on the overall depth of the slab. For slab depth more than 300 mm, the K factor is 1. For slab depth more than 275 and in between 300 to 275, that is 1.05. For 250 it is 1.10. For 225 1.115, that is the value of K. And these are the design shear strength of concrete for percentage of steel. For this is the percentage of steel, 100 AST upon BD means percentage of steel. When the percentage of steel is less than or equal to 0.15%, for M15 grade, that value of design shear strength, that is tau c 0.28, for M20 0.28, for M25 0.29. These are the design strength, shear strength of concrete, that is values of tau c, and these values are given in the problem. Then maximum shear stress of concrete. The maximum shear stress of concrete, that is tau c max, or it can be denoted by tau c limiting. Tau c max is the maximum value of shear stress of concrete which depends upon the grade of concrete. The nominal shear stress tau v should not exceed this tau c max value or tau c value. That is, tau v is less than tau c or tau v is less than tau c max. In this case, there is no shear reinforcement is required, but for avoid diagonal cracks, minimum shear reinforcement is provided. So these are the values of tau c. For concrete grade M15 it is 2.5, for M20 2.8, for M25 3.1. These are the values of tau c. Then minimum shear reinforcement. When tau is less than tau c or tau c max, minimum shear reinforcement in the form of stirrups shall be provided such that, this is a very important formula always asked in question, MSPD question. This is the minimum shear reinforcement required for a beam section, that is ASV upon BSV greater than or equal to 0.4 upon Fy, where ASV total cross sectional area of stirrups legs effective in shear, SV stirrups spacing along the length of the member, B breadth of the beam or breadth of the wave of flanged beam, that is breadth of the beam in case of rectangular section, and flanged for T section or I section, the wave of flange section is considered, that is wave is considered. Then Fy characteristic strength of the stirrups reinforcement in Newton per mm square, which shall not be taken greater than 415 Newton per mm square. Then forms of shear reinforcement. These are the three types of forms of shear reinforcement, that is vertical stirrups, second one inclined stirrups, and third one is bent up bars, that is bent up stirrups. In vertical stirrups, you have to calculate this shear reinforcement as VUS 0.87 Fy ASVD upon SV. For inclined stirrups, it can be calculated by 0.87 Fy ASVD upon SV into bracket sin alpha plus cos alpha. For single bar or single group of parallel bars all bent up at the same cross section, VUS will 0.87 Fy ASV into sin alpha. These are the three types of shear reinforcement provided in the beam section to reduce the shear factor. So generally these vertical stirrups are normally used for reducing the shear, or inclined stirrups, where ASV total cross sectional area of stirrup leg or bent up bars within a distance, SV spacing of the stirrups or bent up bars along the length of the member, tau V nominal shear stress, tau C designed shear strength of the concrete, B breadth of the member, Fy characteristic strength of stirrups or bent up bars, alpha angle between the inclined stirrups or bent up bar and the axis of the member not less than 45 degree, D effective depth. So we'll see the next point in next lecture.